have some sound. Fantastic. Well, welcome to our meeting. We feel as though we should have Bruce Springsteen on here, but unfortunately we've only got session M25, the celebration of 100 years of IAMAS. I'm John Turner, I'm the president of the association, and I'm sure you've seen everywhere that IUGG are 100 years old this year, but IAMAS are also 100. They were founded in 1919 as the section of meteorology in the fledgling IUGG. And over the years, we've changed our names a number of times to IAMAP, then to IAMAS, as the nature of our science has changed and broadened. But we have our origins 100 years ago, so we thought in the Bureau of the Association that we needed to put on some celebration. And people love the science, that's why they come here. So we thought we'd have a morning devoted to outstanding speakers who would look back to the last century, some of the achievements we've had, and where we are at the moment, and a forward look. I mean, who can say what's going to happen in 100 years' time? Who will be standing here and talking about meteorology in 2119? But the next few decades, I think, are very interesting, and we'll consider what might happen then. So our theme is past, present, and future in the atmospheric sciences. We have 6 talks, 30 minutes each, with time perhaps for 2 or 3 questions at the end of each. We have a break at 10, and just before that we will have the presentation of the 2019 Early Career Scientist Medal to Lay B. 30-minute break, then 3 further talks. So IAMAS does a huge range of science. So we had to be a little bit selective, but we thought we'd put talks together on remote sensing of the atmosphere, which spans many interests, and then atmospheric chemistry and pollution, which is a really important and very current topic. Climate change we obviously had to deal with, and we're lucky to have Thomas Stocker to talk about that. IAMAS doesn't just deal with the atmosphere of the Earth. So Athena Kustenis is going to look at the atmosphere of other planets. That should be very interesting. And finally, Andrew Brown will talk about weather forecasting and where that is and where it's going in the future. So to start, we have Jim Fleming from Colby College, and he's going to talk on IAMAS 100 years of research, challenges, and accomplishments. Jim.
Thank you very much. Thank you. Good morning. The 2,000 bagels will arrive at 10, just in time for the presentation, so stick around. It's my pleasure to be here. I don't know if my slides are up. They are. It's a real honor to have been invited to prepare this talk, and I'd like to do it in 2 parts. The first part is things you might know pretty much about the institutional side of IAMAS. And the second part is more intellectual, about certain ideas and principles that went on in the early 20th century. So without further ado, let me see. This is an epigraph from James Espy, who was the first national meteorologist in the US. He was really quite an accomplished theorist of convective storms, and I used it as an epigraph in my first book, but he did it in 1851, and he talked about collaboration. He said the astronomer can sit at the eyepiece of their telescope, but the meteorologist needs to have information from other people. And I think that's the spirit of IAMAS, as far as I picked it up in my interactions, is that we need each other, and we need to work together and develop new techniques and technologies to try to measure and then model the atmosphere. So that's the theme. And so I'll start with the intellectual bare bones, and then I'll work on some intellectual history. There's a long history of international cooperation, and you're going to see in the early part of the talk the word international keeps coming up. We always call everything we do international, but the Accademia del Cimento in Italy, through the Royal Society, there was lots of early efforts to coordinate observations beyond national boundaries. Most of these places reached out away from their political boundaries to get a larger picture of the atmosphere and to make sort of a meteorological optical focus for their weather observations. The National Weather Services began mostly in the 19th century and can date their histories there. But the IMO comes in 1872, and there was a very interesting publication I recommend it highly. It only ran for 10 years or less, run by the U.S. Army Signal Office, called the International Simultaneous Observations Bulletin. And that was an attempt in the 1870s to put all the observations on a map and actually look at it from, in some cases, a polar projection. And I'm going to show you a polar projection map from 1914, just a few months, half a year before World War I broke out, and show the state of where the science really was almost there when the tragedy of the war came along. So our International Science Council, currently named, traces its history back to earlier associations. There's lots of 19th century associations, but one of the largest ones was founded in Germany in 1899, and it ran up until the outbreak of hostilities. I really want to emphasize again that World War I really devastated a lot of what was going on at the time. A lot of creative work was broken. And then after the war, the International Research Council tried to put together international cooperation in science by getting together the nations that worked on the Allied side, and that's what we're celebrating, really. The IUGG was part of that beginnings in 1919. Since then, we have ICSU, which has run for a long time until just last year, and now the encouraging thing for me, a historian, is to see the International Science Council merge with the International Social Science Council and really make an official connection between history, social science, economics, sociology, all those social science and humanistically informed fields, and bring it together with natural science. So I have high hopes for the International Science Council, and I think we need to move forward with we were just talking about having more history involved, more professional history involved in our meetings and training. And I just listed a whole bunch of programs probably many of you were involved in, up through the Human Dimensions Program, the Future Earth, the World Research Program, and Climate. So it's a distinguished umbrella organization, and just so you know, there's an International Union of History and Philosophy of Science that's under the Science Council, and my particular group is called the International Commission on History of Meteorology, so that's what I represent too. This is the polar projection map of January 1st, 1914, about 8 months before World War I broke out. And it looks down on the North Pole, and it's a compilation of different weather services, some from Russia, some from Europe, some from America, mainly those three nations. There was less information from China and Japan. But I took to make it more visible in a lecture, I highlighted the low pressure areas, and I put a little shading on what was called, it was a surface map, but surface lows are shown, and there's 5 of them around the polar projection. So you can imagine that they're getting onto this notion that there are traveling waves around the planet, that they are baroclinic. You can see that word was in play at the time, and you can see that the temperature and pressure lines are not in line with each other. They're crossing each other. And you can imagine the excitement. This was from the U.S. Weather Bureau. But at the time, Wilhelm Bjerknes was working with the Weather Bureau, and there was a real excitement that we could start to get a hemispheric notion of what's going on the planet. This is 3 years before the polar front became a big program in Norway. So just remember that. We're trying to get back to that point. And the IUGG, as we know, and we're celebrating, is 100 years ago in Belgium. They developed the union. And that included meteorology, as well as a bunch of other things. And so they decided not to just be a geological kind of solid Earth and Earth positioning kind of union, but to bring in the atmosphere. And one of my favorite comments was, it was at the International, the IGY, it was the beginning of the International Geophysical Year. An oceanographer got up and said, the oceans cover 70% of the Earth, so they're really, really important. And Harry Wexler, who you'll meet in a minute, he stood up and said, yeah, but the atmosphere covers everything. And so it's really important to understand atmospheric dynamics. The IUGG has a distinguished history. It did not include the nations of Germany, Austria-Hungary, and things after the war. There was a problem with that thing. But Germany developed its own geophysical society. and joined the IUGG in 1939. So another part of the theme of the IUGG is sort of healing political differences. Science is supposed to be international. The laws are supposed to apply around the planet, the different laws of physics and chemistry. And the unions have had some ameliorating effect in bringing people together. This happened in the post-World War I era, when things were really raw, Treaty of Versailles and things like that. But also it happened when Rossby went back to Sweden and tried to bring together the divided nations of Europe in the 1940s. And so that's one of the other things to be proud of, I think, as well as advancing the science. It's also advancing international understanding. And we're still making some progress on that. We still have a ways to go. The IAMAS, it's not working. The IAMAS had its first section of meteorology in Rome and became part of the union. It's had a number of name changes, which actually represent the intellectual history of meteorology, and every one of them has the word international in it, so I thought I'd put it up there for emphasis. The International Union of Association of Meteorology in 1930, the International Association of Meteorology and Atmospheric Physics, 1957, and the International Association of Meteorology and Atmospheric Sciences in 1993. So the quiz today, the prize, the 2,000 bagels goes to who can guess what the name of this association will be in 2119? Okay, so what are we going to be called in the future? Something cosmic, right? And so the stated goal was to advance scientific understanding, so we are the scientific understanding side of things, and to connect efforts to the larger Earth's interactive system. I want to give a special thanks to my good friends and colleagues, Hans Volkert and Mike McCracken, who put together an article like this year. It's come out in the journal History of Geology and Space Science, or Geophysics and Space Science. And it's a century of international cooperation. So if you need to go back and look at the structure of the International Association, you can find information in that article about sections and about the general history of the thing, and anybody who was running the organization. Lots of your pictures are in there, I think. Okay, so I'm going to move to more intellectual topics outside of the structure, and that was somewhat related to the first president, Sir Napier Shaw, who was a very distinguished British meteorologist. He ran the program and, of course, is well known in international circles for his publications. And the first secretary, Charles Marvin, who was actually head of the Weather Bureau. And the typical look at the U.S. Weather Bureau history is that it was run by bureaucrats that weren't very creative. But Marvin actually was very creative, and he made kite anemometers, he made remote sensing devices. And I have a picture of him with his instrumentation, because he was quite a tinker and experimentalist. So these two people gave a kind of an intellectual push to the Bureau of Meteorology at the time. And I have one of these. Yeah. And so Shaw was a very good colleague, associate of Bjerknes. I have a picture of Shaw on the left and Bjerknes just to his right in Bergen consulting. This was in 1920. It was right after the union was formed. And they were meeting in Bergen with the English-speaking group to talk about the future of the polar front ideas and what we could do about air mass analysis and things. And then they had a second meeting in the summer of 1920. The proceedings were in German, held in Bergen. And so there was an attempt, even though the union wouldn't let the Germans into the group, there was an attempt to go back and heal these divisions. Thanks to the article by Hans and Mike, we also have them sitting side by side at a Bergen meeting of the Upper Air Commission in 1921. So I want to emphasize that I think Bjerknes was definitely on the dynamic meteorology side and was developing some of the ideas that I'd like to share with you. So I wrote a book in 2016. It's MIT Press. It's available in paperback now. It's called Inventing Atmospheric Science, and it goes from early dynamics through today's, not really today, but up to about the end of the 20th century, challenges that atmospheric science will be facing. And I based the book, I can't do everybody, and I tried to be international about it. So I have a Norwegian, Wilhelm, a Swede, Carl Gustav, and an American, Harry Wexler. And so it's a choice I made to use 3 generations, each studied with the other. So they're kind of grand students, or students and grand students of one another, Bjerknes, Rossby, and Wexler. And that takes you from about 1900 to about 1960. Wexler died in 63. And you have 62. And you have 3 basic technologies that transformed the whole 20th century. These were not technologies made by meteorologists. These were general use technologies: Marconi wireless, RCA radio, the coming of the radio sonde that's on the cover of the book. The radio family runs through the early digital computers because the radio tubes were the switches and the logic circuits. Aerospace, the Wright brothers get off the ground in 1903, and suddenly the upper air becomes a place for travel, study, airmail, military operations. It becomes important, and meteorology becomes even much more important because of that. And then nuclear. You don't think so much about a nuclear atmospheric science, but the bomb tracers, the debris, the ability to look at the stratosphere and look at global circulation of detritus was a really important stage in atmospheric science. So based on these basic technologies, and then the work in fluid dynamics by Bjerknes, and upper air waves by Rossby, and then Wexler, who was head of research in the Weather Bureau, pulling together the new technologies and applying them to meteorology. That forms the core of the book, and that's what I'd like to talk about for a few minutes. So Bjerknes is a leading protagonist, I just said that. Rossby was his somewhat student. He spent a couple years in Bergen, but was basically his own person and went off to the US and developed the department at MIT and then at Chicago, and went back to Sweden in the 1940s to try to heal the World War II divisions that were still raw in the society. And then Wexler was a Rossby student who went to MIT and studied there and became the head of, and I make a kind of a Christopher Robin 100-acre wood analogy, where a lot of histories that I've read, at least, the ones about the US Weather Bureau were about the bureaucrats who couldn't get much progress forward and how they opposed the Bergen program. And there's really a different interpretation, and that is kind of Rossby and Wexler is sort of Christopher Robin in the 100-acre woods saying, wow, we got radio now. Wow, we got radar. Geez, we can get some V2s up to near outer space. Look at this digital computer they're making. They're sort of playing with these ideas, and almost immediately after they make a debut in a general computing history book, you find that it's being applied to meteorology, for example, at the Institute for Advanced Study with Johnny van Neumann. And so the history of general technology and the history of meteorology are pretty much fused through these kind of techniques. There's another sub-theme, which is military, which is the military really wants to be able to prevail in the atmospheric environment. So some of that is driving the research as well. The 3 leading protagonists, and then what I call the Gordian knot of meteorology. The Gordian knot's a famous story about Alexander the Great, and there was a knot that couldn't be untied. And so Alexander drew his sword and just sliced it in half and said, there, I solved it. And so in a way, technology is sort of our Alexandrian sword cutting through the Gordian knot. But I think there's a new knot in town, and I'm going to get to that in a moment. The new knot is chaos, and the ability to slice through the chaotic limits of forecasting is something we have to still confront. So the Gordian knot was the Gordian knot of meteorology was that intractable, intertwined tangle of observational imprecision, theoretical uncertainties, and nonlinear influences that if you could unravel it would provide perfect prevision or forecast of the weather for 10 days, seasonal conditions for the next year, and climatic conditions for a decade or longer. Wouldn't policymakers love to have that? Wouldn't they love to have your perfectly polished crystal ball? But we know we can't do that. When I teach weather, climate, and society, I have my students in the first week look ahead a week or 10 days, make a record of the future forecast, and then see how it actually verifies. And a lot of times it doesn't quite match up so well, or at least after the seventh day. So we have to deal with this idea of a chaotic limit to forecasting. And this is something that was known, I think, to Wilhelm Bjerknes at the turn of the 20th century. So Wilhelm had what I call a neo-Laplacian program. Laplacian program would be, you give me the positions, I'll give you the final result. It's an exact one-to-one match between laws of physics and initial positions. And Bjerknes published in 1904 an article in the Meteorologische Zeitschrift where he said, here's the program to make meteorology an exact branch of physics. We need sufficiently accurate knowledge of the state of the atmosphere, and then we need sufficiently accurate knowledge of the laws so that we can take the next time step. And when I read this, the word sufficiently is not italicized in the bulletin. But when I read the article, the word sufficiently just popped out at me. And it was like, yes, sufficiently. Bjerknes had studied with Henri Poincaré in Paris. He knew that we couldn't have exact measurements of every variable, every little wind gust, and every little temperature fluctuation. And he knew that the laws were approximately exact. We knew he was getting the 7 laws organized at the time. And so he said, let's take the diagnosis issue at hand and let's do the prognosis issue. And the best we can do is make a useful graphical integration of what we have for our observations. So he put the central problem of meteorology on the radar there as weather prediction by rational theoretical physical methods. I think that's one of the things we're still trying to do. I don't have any timer running here, so what time do you want me to quit? 5 more minutes? Oh, you'll give me 5, okay. Okay, so Bjerknes travels actually at the time he was in Stockholm. This is before he got to Norway. He travels to Columbia University in 1905, and he shows a U.S. weather map. And this weather map's very static. It has winds, temperatures, observations at stations across the country. And Bjerknes basically connects the dots. He says, what if we made trajectories out of these numbers? And we show that there's a call and there's a flow going into Minneapolis there in the upper Midwest. And what if we had a transcontinental balloon travel and a big dirigible was coming in from the west? It wouldn't want to fly straight into Minneapolis. It would want to go south and be pulled in by the winds. So he was thinking very practically. Bjerknes gave 2 major lectures to big public audiences in his lifetime. One was how the weather works, and one was how airplanes fly. So he was working on aerodynamics and dynamic meteorology and putting the two together in 1905 when he began writing his textbooks on statics, kinematics, and eventually dynamics. So there's a pre-Bergen School history that's usually not discussed much. You'll find some of the details in my book. And then there's Bergen School. As Bjerknes left, he was in Germany and in Leipzig during the World War I, and he moved to Norway with his son, Jakob, and with a brilliant associate named Tor Bergeron, who wrote up the history of the Bergen School. And this comes from Bergeron's version, that what you need to make a forecast are sufficient observations, and they had a very dense network along the coast of Norway and in the mountains and on the fisher boats. And then what you need is a tool to analyze those observations objectively. His tool was to put in the streamlines and to look at the rain patterns here in Bergen. And then he said it doesn't hurt to have a model which can help you move into a forecast. What's the next step in this ideal model? So the Bergen model is very familiar. I'm not going to dwell with that. But they talked about OTM, observations, tools, and models. I think we still need to keep that in mind as we move forward. Rossby was an acolyte of the Bergen School. He moved to America, came on a Weather Bureau fellowship, and one of the first things he did was in the basement of the Weather Bureau, he made a rotating tank, a wave tank, to try to show the circumpolar development of fluid motion around a differentially heated rotating tank. This is something from the 1930s, much earlier than you usually think of the Fultz experiments in Chicago. So Rossby tried to get this thing working and basically was able to understand planetary Rossby waves. Again, it's a long history, but I'll keep it short for the morning. And here's a 5-wave pattern. Now think back to 1914. I mean, were getting to that point where possibly with upper air measurements they could start to draw these kind of pictures in 1914. But now they were able to think about it theoretically and develop the 5, 6, whatever standing waves around the planet. The technologies I mentioned were the radio family. Here's Marconi sending information without wires across the Atlantic, and it became immediately adopted by the weather services. Robert Fessenden and the U.S. Weather Bureau developed a Marconi station within 2 years after Marconi's announcements. The aviation family, so I have the Wright brothers getting off the ground, heavier than air. Heavier than air means you can take up some instruments, you can start to do some measurements, you can start to develop the commercial and military use of aviation. And then the bomb with all of its tracers. And so the ancestor, the descendant of Marconi is the radio son to miniaturize radio, send it aloft, and not have to worry about spooling a kite and bringing it up and down, or having the measurements come back down and take a measurement from a recording device, but have the radio. And the radio operator here, this immediately led Rossby to put electronics into the meteorology curriculum. So the guys at MIT, they had to study their dynamics, but they had to take courses in electronics as well in order to run the new equipment. Then the airplanes improved. This is an image of Wexler's flight in a World War II era plane into a hurricane off the Atlantic coast. And then this is a special projects unit that tried to use trajectories to find out where the Russians had set off an atomic weapon in the middle of Asia. So in the Russian country, then they traced the tracers back and made a dynamic map of radioactive fallout. Another descendant of radio is radar, and that developed early in the war. Also, the ENIAC computer. There's von Neumann, the head of the Institute group, and Wexler next to him, with Jewel Charney over here. I got a lot of flack for why didn't I pick Charney as one of my 3 protagonists, and it's because Charney and Rossby did a lot of the same things, and there's already been work on Charney. So I picked Wexler as a kind of the Christopher Robin of the book. And then there's the captured V2s, getting up to near space, expanding the idea of what is the atmosphere from surface weather into the middle atmosphere and then even to the edge of space and then into space. So Wexler was the chief scientist for the TIROS project. He was the first spokesperson and developed the TIROS weather satellites. In 1956, Rossby said, technology is cutting the Gordian knot. This is a new Alexandrian sword where we can see the nowcast in a way. We could start to see the radar echoes. We could start to see from space. We have eyes in the sky coming up, or at least through the IGY. And that's when we changed the name of the association to atmospheric physics. I think it helps recognize this great technological leap that we've taken in the 20th century. The radio family, I've already talked about that. The aerospace family, up through satellites. And then the nuclear family, which we're not currently testing in the atmosphere, probably thank goodness, but it did give us quite a picture of what was happening in the upper atmosphere. There's Wexler and Rossby at Woods Hole. They had summer institutes. They were close colleagues. There's Wexler and Life magazine looking at the TIROS pictures of grainy, fuzzy satellite photos. But next to him is a Bjerknes-style analyzed weather map with fronts on it. So they tried to put the Bergen analysis on top of the TIROS pictures, and he's kind of being Sherlock Holmes here for the Life photographer looking at the pictures. There's Wexler and Bagayev in Russia negotiating the World Weather Watch, and so it was also part of scientific diplomacy. The 2 satellite nations at the time were trying to share their information with the rest of the world. And then there's Rossby, who went back to Sweden, kind of a bon vivant, always the center of a moving seminar, a good guy to be with, and he's happy to be back in Sweden to do his international institute there. And with Bert Bolin, who we heard about a little bit last night at our dinner, and Bolin becomes a central figure in some of the environmental materials. Rossby's actually said he's worked on the computers, he's worked on the dynamics, now he wanted to work on the big issues of atmospheric chemistry and the Earth system into the future. And so we move in this era from meteorology to atmospheric science. I'm going to assume you can read faster than I could speak about this, but basically it was run by committee. It became, in the Cold War era, especially around the time of the International Geophysical Year, through the work of people like Lloyd Birkner in the US, there's a lot of new money and a lot of new efforts to bring atmospheric science family together. The cloud physics, the cloud chemistry, the climate issues came together and became atmospheric science. So what did we do? We changed our name to And Atmospheric Science. That's how IAMAS came together. Here's an interesting shot of the Earth's atmosphere. If you go to NCAR in Boulder and you stand in the lobby, you can look up a couple stories and see this big depiction of the Earth's atmosphere from the surface, where Bjerknes worked mainly, didn't have much atmosphere, upper atmosphere. Where Rossby worked, he actually got his airplanes up off the ground and his radiosondes. And then where Wexler worked with the satellites. So the name atmosphere is a shape-shifting noun. It doesn't mean the same thing for 1900 as it does for 1960 and later. And so atmosphere is from the surface of the planet to the surface of the sun now, at least, and maybe further out. And so I'm going to wrap up now. In 1960, Wexler co-authored a statement that the goal of meteorology with all this new technology is to portray everything atmospheric, everywhere, always. That's quite a challenge, everything atmospheric. And the same year, Ed Lorenz was in Tokyo talking about chaos and says, well, maybe. I don't think all your technology can push you into the perfect future. So you know about Lorenz, but I wanted to mention the climate of his simple model was basically not driven by external conditions. It was driven by fluctuations in the data. And so an emerging property of climate has to be considered. Final thoughts, I'm going to let you buy or read or write to me and ask for the book. But was Bjerknes right with his sufficiently accurate knowledge of the state of the atmosphere? Was he right about sufficiently accurate knowledge of the laws? I think so, but it was that sufficiently word that really has me going. And so I would say that the best path forward is continuous, technologically enhanced, real-time measurement and monitoring of the atmosphere and oceans at every scale, sufficient to provide feedback and diagnosis for improved models. So we have to have that link between remote sensing and modeling and back and forth and spaghetti plots and all that. Okay, well, thanks for your attention. I'm ending at this point. Thank you. I wanted to thank you very much. I wanted to congratulate John and Terry for their getting an award for being IMS leaders, and I want to say happy anniversary. So thank you for your attention.
Okay. Just time for a question or two. Any questions? One down there. Hans.
I know Hans.
Well, thank you very much, Jim, for this very far-reaching 100-year-long presentation. I just want to remind us, which you certainly know, that Carl Gustav Rossby was the president of IAMAS, YAMAP, then in 1957, and then it was planned to have an IOGG meeting in Toronto, I think, in the September. Unfortunately, as he was working so hard, 14 days before, he had a heart attack in his office and could not make it, and similar happened, I think, to Wexler. I think these people somehow were really overworking themselves, I think, for the atmosphere. But I think the relations to YAMAS and YAMAS is very close, much closer than you said, I think, in your presentation. Just a little adding comment.
Somebody asked me once, what would you say to Harry Wexler if you could see him? And I'd say, Harry, slow down, take it easy. And same thing with Rossby. Thank you for that comment.
I think we have to move on.
That's fine.
Thank you very much. And perhaps any more questions you can ask Jim in the break. So next we turn to remote sensing. BJ Sohn from Seoul National University in South Korea, who's going to talk about satellites, remote sensing achievements, challenges, and future progress. BJ.
My name is BJ Sohn, and I'm from Seoul National University. It is my great honor and pleasure to celebrate the 100th anniversary while giving this satellite remote sensing talk. Best wishes to IAMAS be making successful in next century. The talk I would like to bring about brief history of meteorological satellites, then I'd like to make some highlights about the key findings and scientific advances, mainly focusing on climate weather applications, not really land and ocean applications. This is very brief overviews. Therefore, I cannot go in detail to the scientific advances, great achievement. Then later, I'd like to provide some kind of outlook, how we are going to maintain the satellite program or get the maximum out of satellite information to enhance scientific achievement. I think the beginning of the weather satellite or satellite meteorology emerged in the late 1950s during the Cold War period. As you see on the left side, that is a picture of the first man-made satellite, Sputnik 1, which was launched October 4th of 1957. It was 83.6 kilograms, which is really dwarf comparing to current satellites. Then the follow one is Sputnik 2 is a little heavier and carried the dog on board. Really, space race started when the U.S. launched the Explorer 1 on January 31st, 1958. That really discovered well-known Van Allen radiation belt. Since then, the first weather satellite has been flown in 1960 because of gradual improvement has been made in instrumentation and other technologies as well. So first satellite called ATS-1 was launched from Cape Canaveral and lived 77 days. That time, the satellite carried 2 TV cameras, 2 video recorders, and power other communication systems needed for really communication with the Earth's surface. So that was a really exciting moment in the satellite history because it was the first time to see the cloud moving over ocean and over the continent. I think that's the picture the Professor Wexler saw with the magnifier. And on the other hand, newspapers joined kind of headlines. For example, U.S. Weather Eye satellite in orbit. So Weather Eye. Then Washington Post sees that the satellite maps weather from 450 miles in space. So that's a really exciting moment. People can see weather from the space. Later, because of kind of imaging possibility of weather, the interest was shifted to first geostationary satellite. So first, the geostationary satellite was flown in 1966 called ATS. I'm sorry, the previous one is Tyros. I like to make correction. This is ATS-1, launched on 6th December of 1966 into the first geostationary orbit. Since then, it's just revolutionized satellite meteorology with spin scan camera. The Professor Sumi, who is known to be a father of satellite meteorology, once said that you can see the clouds move, not the satellite. So it is kind of instant replay of any football game or any kind of movie. Now ubiquitous everywhere in the world. Suddenly the scientists could see the weather moving around the continent and hemisphere, really revolutionized the weather forecasting forever until now. Then after 60 years from the satellite, we have so many satellites here. If you take a look at the old satellite images, now in the space, you have a lot of polar orbiting satellites here. I think from, I cannot see very well, but from GPM to really JASON, European satellite, and the polar orbiting satellites. On the other hand, on the geostationary orbit, there are many satellites as well. So GOES, American satellite, and Japanese Himawari, and Korean COMS GK2A, Chinese FY series, and European, there's Indian INSAT, and the European Meteorosat series. So we have many satellites now dedicated to weather, climate, and environmental observations. Now it became very indispensable part of Earth's observing system. So, after 60 years from the first satellite, now we have the satellite capability to measure with a finer spatial resolution and finer forecasting scan. Oops. Show you here. Oh, there's movie, but I cannot display. But there's a lightning image overlaid with cloud imagery taken from GOES 17 satellite. Although I don't show the kind of movie showing the movement of the convective system, while the lighting images are really following the system. So we are now capable of measuring every bit of weather event and climate signal of the globe. So that is a great achievement we have after 60 years of first weather satellite. So what we achieved in the last 60 years, I gave some highlights in the matter of what we consider great achievement in satellite meteorology. First thing we considered might be profiling, getting the temperature and the moisture information from satellite. The concept has been developed as early as the 1930s when Chapman introduced the concept of weighting function. He tried to show why the ozone layer is in the stratosphere by introducing the maximum absorption of radiation, which is in fact very similar to the concept of today's weighting function. But the Kaplan was the first person who pointed out the possibility of gaining the vertical information from the spectral domain. So he said, quote, three-dimensional distribution of temperature and the water vapor can be obtained from the spectral variation of its thermal radiation. So later, Bill Smith and other scientists tried to get those information from the limited channel information. For example, Smith, as of 1970, he tried to get the temperature profile from 9 or 10 channels. But today, we have hundreds of channels available to us, such as sounders like AIRS, ERC, CRIS, GRIS, GERS, and IRS. But even so, the profiling itself is a very challenging problem because it is mathematically ill-posed. So still, depending on what initial gas we use. I think the weather forecasting would be foremost achievement we can address. I'd like to show how the forecasting skill has been improved for the last 38 years from 1981. That's ECMWF 500 geopotential anomaly prediction, depending on the weather forecasting range from 3 days to 10 days. But the line in the upper one is for northern hemisphere and low one is for southern hemisphere. So during the 38 period, there are many elements contributed to such increasing forecasting skill. For example, 3-day started from nearly 87% and nowadays nearly 98%. During the meantime, as you see in the bottom, the model resolution has been really improved from 210K to 8 to 10 kilometer. So there are many things contribute, but there's no compelling evidence how these two can be merged around 2000 onward, except the use of satellite information. Interestingly, for the total forecasting sensitivity to observation impact by instrument tells that the microwave water vapor and temperature are the biggest two contributors. And there's aircraft and infrared temperature, atmospheric motion factor. These are also infrared water vapor satellite measurement. Therefore, there is great amount of contribution is coming from satellite contribution. But in doing so, through the direct assimilation of radiances into NWP system, like great work by John Ayer about direct assimilation, he mentioned that in recent years, difficulties has been experienced in exploiting satellite sounding data in numerical weather prediction and NWP in the form of independently retrieved temperature and humidity profiles. So they started to really assimilate radiances directly into the weather forecasting assimilation system. Of course, today, we still see the direct use of a product as well, like atmospheric motion vector, actually realizing the idea of Professor Sumi. Other thing I'd like to mention about great advances would be Cloud-Aerosol Interactions. On the right-hand side, it shows difficulties of simulating the global temperature trend under the global warming era from 1860 to current years. For example, this observation, and the red one is for carbon dioxide, the only simulation. But when they added sulfate direct effect into CO2 addition, then the simulation seems to be picking up the observation, not quietly catching these bumping features. But it was satellite observation which led Jim Coakley to think about aerosols' indirect effect, as shown in this figure of the marine stratocumulus area off the west coast of the United States by ship plumes. Later, Nakajima and King, they were able to estimate cloud optical thickness as well as refractive radius from using two-channel approach here, visible and near infrared. With great achievement, great success of MODIS experiment, we are now able to get the global pictures of aerosol optical thickness and cloud effective radius, which can have pictures of aerosol's indirect and direct effect. So we can better simulate the climate prediction now with such contribution. And those achievements seems to be accelerated with possible active remote sensing from the space. For example, the rainfall measuring mission like a TRIM and the currently GPM, and aerosol profiling, Calypso, and the cloud profiling, CloudSat, they're all in the constellation mode, coincident in space and time. Those contributions is now make us possible to get the global as well as the vertical features of water vapor and the cloud fraction, evaporation, surface rainfall, even further getting into the real answer of aerosol cloud precipitation interactions, which is a really important subject in the global climate change. And of course, radiation budget is the core scientific objectives from the beginning of the satellite program. Because radiation is a kind of ultimate energy source, driving general circulation as well as the controlling climate change. So that's the genuine interest why we have to measure radiation budget. The first really successful radiometer was flown with Explorer 7 when Professor Sumi put the black and white ball radiometer in the space. So that was able to measure global albedo as well as global long-wave radiation emitting into the space. But great achievement has been made when we went through Nimbus experiment, through Nimbus 6 and Nimbus 7 here. So long wave and short wave, solar and net radiation of the global domain really helped us to understand the global distribution of radiation, where the sink is, where the surplus is. With development of further capability of measuring the radiation, then early experiment gave very important result, such as kind of reference giving to GCM models or the cloud radiative effect. The first time we really quantized the magnitude of cooling. So cloud can give like a cooling effect of about 20 watt per square meters. Now, with serious experiment, we can have a better idea where the climate change signal is. Even we are able to see the energy imbalance and the planetary heat uptake, such as the paper published by Lohmann Loeb et al. So that's the really great moment we see the radiation budget and the imbalance now. Of course, the air pollution is another thing. Really, we get the benefit from satellite measurement. Here, also I'd like to emphasize the global constellation or collaboration. As shown here, geostationary observation network. Here on the globe, there's TEMPO, NASA TEMPO, and European ESA, Sentinel-4, GEMS, Korean GEMS. They're all the geostationary sensor which can measure aerosols and gaseous emission of the continent, of the globe. So they are forming a constellation for common objectives, like measuring the aerosols and monitoring the gaseous emission, and studying the large-scale transport between Asia and Europe and North America, which all have like nominal 8 kilometer spatial resolution and 1 hour temporal resolution. So that is a great success of global aligned constellation. The recent news about the Korean GEMS is that it will be launched, planned around February of next year. So we'll see the global view of emission of pollutant and the transport of those pollutant. And also I'd like to point out the importance of continuous measurement with intercalibrated satellites. For example, we have long satellite information archived somewhere. On the left-hand side, there are 14 satellites measuring the microwave brightness temperatures from DMSP SSMI to current GPM. But to get the really climate information out of those different satellites, we need homogenization and the recalibration of those data sets. So for example, Bergen School, they all recalibrated against current GPM, which has a better calibration capability. In doing that, they could generate like a 30 and plus years of all the SSMI like microwave data from which we can derive various fundamental climate variables like water vapor and precipitation, cloud or liquid water and surface wind, and many other things. Using those information, I studied the snow ice interface temperature retrieval of the Arctic. This is Arctic picture from 1988 but I show until 2011, but it produced until 2018. If you see, this is the temperature of ice top layer below the snow level. So we could see all the temporal evolution of the temperature of the ice top layer. In the early days, around the 1980s, 1990s, you see the very cold temperature there. But recently, you see very warm. Surprisingly, the temperature rise really 9K for 30 years. Really tremendous amount of temperature increase over the Arctic. So with this, looking back over the last 60 years, there were great achievements from satellite remote sensing, measurement, different satellite missions. But it is very hard to imagine what comes next in the future when we consider really in this rapidly changing and evolving information age. But at least we can address some of important issues as WSRP Grand Challenges defined. There's only one example of many scientific objectives, such as melting ice and global consequences, clouds, circulation and climate sensitivity, carbon feedback in the climate system, weather and climate extremes, water for food basket over the world, regional sea level change and coastal impact, near-term climate prediction. There can be very small items out of many things we can address in terms of satellite measurement. I'm pretty sure in the future, satellite remote sensing and satellite meteorology will be very successful and continuously providing scientific advances in the future, understanding weather and climate change as well. In doing so, we need to continue and enhance operational polar geostationary missions as the pillars of global space-based observing system for weather monitoring and prediction. In doing so, we need a better calibration and characterization of instruments. And we need a higher spectral resolution, such as reducing signal to noise ratio. And we need observations I need for NWP system as guidance, okay? And we need important observation sensors like 3D wind field with Doppler LiDAR. And for the climate monitoring, continue observations of essential climate variables, reprocess archive satellite data, and continue and enhance existing climate records. Of course, we need absolutely calibrate reference, such as CLARIO mission. And we need to better understand Earth system processes, for instance, hydrological cycle. This requires integrated observation of geophysical parameters, such as continuation of A-train constellation and active measurement, cloud radars and cloud lidars, aerosol lidars from space. And also we have to enhance spatial sampling, resolving the time scales of precipitation process, probably with the help of CubeSat. With many CubeSat, we could measure three-dimensional the water cycle information from space. And we need to advance observation of the atmospheric composition air quality by continuously running the GEMS and TEMPO Sentinel Pole-like geostationary orbit sensors. Finally, we need advanced carbon cycles like extending OCO, GOSAT, and TANSAT missions with advanced instruments. So we have to consider extension and expansion through the international cooperation. That's very important. One country cannot do everything. So we have to spend our energy and resources to reach the common goals through the international cooperation. That's the message I would like to say. This scientific knowledge should not be protected by any means, by any countries. Thank you for that. But before doing that, I'd like to say about the IAMAS 2001, Busan, Korea, which is exactly 1 year after from now, 18th to 23rd July 2020 on. Welcome to Busan, Korea, next time. Thank you.
Time for one quick question from the floor, perhaps. Anyone? If not, thank you for your very clear presentation. Thank you. So the final talk before the break is by John Burrows from the University of Bremen, who's going to talk on changing atmospheric pollution and chemistry observed from space in the Anthropocene. John.
First of all, I'd like to thank the IAMAS team for inviting me to give this presentation. It's a great honor. IAMAS is 100 years old, like IUGG, and actually the commission that I've belonged to for a number of years, IACACGP, is actually now 61 years old. So we've been working on a lot of things. Now, my talk fits very nicely around the two previous talks, in that I'm going to talk a little bit more focused on a particular area, which I think is of great importance in this new geological epoch that we're in, the Anthropocene. And the Rosby Institution was, of course, a very important institute, and my mentor and leader, Paul Crutzen, came from there, and I'll be talking about some of his stuff. Anyway, a lot of people helped me to make this talk. This is a picture of ENVISAT, which has SkyMachi, and SkyMachi is a project and a satellite instrument which I started a long time ago now. It means doing the impossible task, fighting shadows, things like that. And it's sitting on ENVISAT, which is the galleon sort of European remote sensing. Now, European remote sensing, I just wonder how does the, okay, so just looking at the geological timescale, humans have been for a very short period of time on the Earth. I mean, Earth started about 4.6 billion years ago. The solar system formed, and life started somewhere between 3.5 and 4 billion years ago, and possibly 200,000 years ago or so, Homo sapiens showed up. Okay, but and initially they were kind of riding along as a passenger on planet Earth, but now we're kind of dominating things, and in particular since the Industrial Revolution. So, well, first of all, the Neolithic Revolution, there were about 4 million hunter and gatherers. The first settlements then came, and population rose by quite a lot to about 1 billion in 1800. And now it's about 7.6 billion. We've got more than 50% of people living in cities since about 2011 or so. And the tendency is to go to 10 billion, and megacities and human population is going more and more. And this is now such that we are dominating the planet Earth. And that's why Crutzen, in particular, popularized and came up with the idea, also Stürmer, of calling this new period the Anthropocene. Okay, when you look at population of the Earth, you can see that it's actually very different from the geographical representation in terms of size. So here's the size of nations with respect to population. And when everybody has the standard of living in Montreal and North America, we're going to really impact even more the Earth, because we need large amounts of energy to do this. And this is the problem. The energy generation makes lots of emissions which impact on the atmosphere. And for about 50 years now, we've been aware of this as a problem, a little bit over, in 1948, or possibly a bit longer. I'll come back to that. But this great acceleration, so maybe the issue in the Anthropocene is when did it start? There's a big debate about that, kind of intellectual debate. Maybe it doesn't really matter, but probably I'd go with Crutzen's suggestion of about 1950 when this acceleration took up. But there's about half a dozen options. And what you see is that everything is increasing, including McDonald's, restaurants, if you look at those curves on the right-hand side. But bad things like ozone loss started getting going, okay? That's the general impression. And things like CO2, methane are really increasing. There's lots of nice pictures in the literature about this. That's just one set. Okay, so summarizing what I just said, we've had a great population growth. It's a smart idea to give something a name. Paul Crutzen's a very smart person, and then came up with it and popularized it in particular. Stürmer was also involved in this. And basically, we need to measure the long-lived greenhouse gases, and we need to measure what are called short-lived climate pollutants. And it turns out measuring these from space is really important. And in general, you cannot manage what you do not measure. So actually, measurements are absolutely essential to understand the changes, because our science is driven by, and the science I've been involved in is driven by measurement, which is not understood by model, rather than model prediction and then going searching for it. It's not like the Higgs boson. Everything in my science area goes differently. We find something like an ozone hole, and we're, my God, what the hell is that? And why did that happen? And that's the sort of, it's a completely different set. Now, maybe we're changing to the theoreticians dominating us, but at present, we experimentalists have had a good run for our money. Okay, so if you're going to measure from space, which I think is essential, and you can actually measure trends, and the point about this is you get the global view. And then you can measure, you can actually do all sorts of different measurements, but in particularly important are low Earth orbit, which are often in sun synchronous or asynchronous measurements, which give you in essentially one time of day at the equator. The other look is, we've heard about this already, the geostationary, which is just coming up now in terms of giving us the ability to look for about a third of the Earth if you spend the money on it. Currently, as you saw from the last talk, we're only getting about a sixth of the Earth because money's tight. And you can then get diurnal variations. Okay, but where are we in general? The past it's a bit like this. I often look out of my window and I can see a drop tower in fog just about. And good scientists like Crutzen and others, they see the tower even when it's really foggy. But the rest of us prefer to have really good measurements like the ones here, okay, shown at the bottom, okay, but we're very much in an ongoing progress to get to that stage. We can just about see the clouds on these pictures, and we're going to move forward, hopefully. In the present, we're getting better, and we need to move forward. We need to have fit-for-purpose measurements. Okay, so when I, as a lab person, got involved in this, I recognized that we could do electronic vibrational rotational spectroscopy to measure fingerprints of species. Not every species can be measured in the gas phase, but it turns out that quite a few can, and a lot of them happen to be important ones, like ozone and NO2. And it turns out vibrational rotational spectroscopy in the overtone bands of CO2, methane, and CO, which my friend and colleague Jim Drummond had already recognized, turns out to be a very good way to measure CO2 and methane from space. But nobody, of course, believed that it would work, and we had endless problems about trying to get this funded and done, but actually SkyMatchy came off. Fortunately, it's sort of fortunate in bad fortune. The Ozone Hole, which was 11% funded by Germany, resulted in Germany feeling that they would like to pay for some of that and started the program. Okay, because about 11% of the CFCs were actually made in Germany, Europe about 30%. So what we're trying to do in the SciMaCI world is use what other people have already done. NASA's program of nadir and limb sounding was already well underway. You have to remember that after the Second World War, Europe was pretty battered, and it took a while for it to get together in terms of making satellites and competing. So although we had, with Dobson and Chapman and all this fantastic European development in atmospheric science, there was a kind of a bit of a pause during which the satellite was taken over by either the US program or the Russian program. But I have to say the Canadians, we're in Canada, they actually shot the third satellite up, and it was an atmospheric one in the 1962 or something. So there are many nations involved in that. Anyway, this is what we want to try and do. We want to measure by looking down, or we want to measure in the limb to get profiles. That's particularly important for the ozone, because most of the ozone's in the stratosphere, and you have to understand it by looking at it at the right. All this is about temporal, it's about sampling. It's essentially first semester physics. If you can't sample the thing properly, you can't see what the hell's going on. So sampling is essential. I know this joke about, so 3 Swiss people are going through a field and they see a cow. One's a mathematician, one's a physicist, and one's an astronomer. And the astronomer says, okay, all cows in Switzerland are black and white. Okay? And the mathematician says, no, one cow in Switzerland is black and white. And the physicist says, no, only one side of one cow in Switzerland is black and white, okay? So theory is good, but you have to actually have the data to be able to do it, okay? And I'm more on the physicist side. Okay, if we can go forward. Okay, so there's a long history, but essentially we proposed it, we've had lots of ups and downs. And the current generation, which is follow instruments, is now called Sentinel-5P, and we're hoping to have the Sentinels. The Sentinel-4 is Geoskier, we originally proposed, and we're hoping to have a CO2M mission, which is CO2 and methane, which was following on from SciMaCI, and a carbon sat, which didn't get selected for an Earth Explorer, but its results are being used for this CO2M. Anyway, it's a real big battle, and you have to keep going at it to get these things up there. But when you get them up there, you get some interesting results. And I just want to start off on to say, okay, this is what we've got. This summarizes the type of things we've got. We started essentially in Europe in 1995, and we have GOME, SkyMatchy, then GOME2 on METOP series, which is EUMETSAT, ESA, and then the Sentinels are starting in the next time on Meteosat 3rd generation with Sentinel-4, and with the follow-on to GOME2, which is called Sentinel-5. and we have this sort of gap filler Sentinel-5P, which is, and all the time we're going into this higher spatial resolution. In nadir. In LIM, I'm afraid the situation is not so good because the LIM sounders, MIPAS, Saimaki, and GOMOS on MBSAT, and the AURA instrument MLS, which is still working, there's no follow-on to those things. So we're really missing actually the vertical resolution in the stratosphere in the next time. Sometime these things are going to stop. We have got just ozone and aerosol with OML, which is an operational NASA mission, OMPS LIM, but it's not very good. We're missing essential data in the future. Anyway, I'm just highlighting that's what's coming in terms of LIM. It's actually up there already. But our work is a little bit driven by policy in this sense. So it turns out that the ozone hole, the loss of ozone, was first recognized towards the end of the 1960s by Paul Crutzen and Harold Johnson, who recognized that, first of all, that the NOx cycle was a dominant controlling mechanism for ozone in the stratosphere. And if you change, for example, by putting stratospheric aircraft into it, you have a problem, potentially. It turns out to be a bit more complicated than that, but currently the issue is that laughing gas, N2O, is increasing, and that's going to be a double whammy in the next century. But the big one was, of course, Maria and Roland's proposal that CFCs, long-lived in the troposphere like N2O, would result in chlorine-destroying substance, chlorine-destroying atoms, CLOs and CL, chlorine monoxide and chlorine. And that was assumed to take place probably in mid-latitudes, mainly at maybe 35 to 40 kilometers or something like that. And then suddenly, Farman at the British Antarctic Survey discovered the ozone hole. It was actually probably John Shankle who first saw it, but Brian Gardner and Joe Farman had been making measurements since the IGY. He was a real fanatic for that kind of stuff, and he put the instrument in, and it was his kind of baby with his team, and it produced a unique result. Anyway, we understand this chemistry now. There was a huge effort, particularly in America, to understand with aircraft experiments. It's all fantastic stuff, but basically just summarizing, when these long-lived tropospheric species release chlorine and stuff like this, you get temporary reservoirs like chlorine nitrate and HCl, which under the condition of polar stratospheric clouds produce chlorine and bromine chloride, and they photolize in spring, and then there's a release of halogen atoms which removes ozone in about 60 days. We understand this, and the question now is what are the dynamics doing it and drawing it? Now, what you can see here is a nice picture from Mark Weber and my group of our version of this is the October monthly, the last large ozone hole. It's still there. The question is, it's supposed to come back at some point because Montreal Protocol is a big success story. However, it's still at this stage where holes are quite prevalent, okay? And in this context, you can see the activating species OCLO, which can be measured from GOM and GOM2 and Saimaki, etc. And what you see is it builds up. And basically, this is related to CL and CLO. It's made in a reaction between CLO and BRO, but it indicates the activity of chlorine. At the same time, during these periods, the oxides of nitrogen are really low. Okay, that's a necessary condition for this hole. So let's just take a look at that. Fortunately, in the northern hemisphere, for us, the dynamics is such that you don't have enough time of stable vortex. So dynamics is controlling chemistry, and we're lucky that we only in a few years have had a big loss. Otherwise, we would have had much more UV skin problems here because, of course, the ozone protects us from biologically damaging UVB radiation. It's also in the troposphere a toxic gas and a greenhouse gas. And that's the situation in the northern hemisphere, more complicated. Occasional years we get quite a lot of CLO, but it doesn't last as long because the dynamics breaks up the vortex in the northern hemisphere. Okay, that's NO2 showing the same picture. Last point I'd like to make, this is now trends using OMPS and SkyMatchy data and SAGE2 data. what you can see, what you can see is that before 1997 we were having the loss in these mid-latitude regions as we expect, and then after the Montreal Protocol bingo, we start to get increases. But it's a bit more complicated than that because we're seeing some unknown, unexplained longitudinal patterns, which is maybe dynamics again. We'll see. So lots of stuff to go on there. That's just a better view of it. Next problem is air pollution. It's also not so much a new problem. Edward the First, he beat up on the Scots all the time in history, but he also had a wife who didn't like air pollution in London, and so he tried to clean it up in no success, and eventually we got the London winter smogs, and then the Los Angeles, in around 1948, Los Angeles summer smogs. And the very bad winter of 1952 is shown here where the policeman is standing. That caused about 10,000 deaths and created the first Clean Air Act in the world, and that's followed around the rest of the world. And you can see some nice places, and you see now that this summer smog type phenomena, which is related to, well, it's complex chemistry. I'll show it in a little bit, and I'm sure you'll understand it. But basically, this is a global phenomenon now, and we see it even in clean places like Spitsbergen, okay, which is, you see there, it drifting in. Okay, so this also is really important because these molecules and pollutants have a big impact on health. Estimate is 3.5 to 7 million premature deaths from this. There's a lot of debate about that. This is now the chemistry that you all learn in my lectures, and it's dead easy. One on the left-hand side, you're making ozone, basically. On the right-hand side, you're making aerosols of different types. And the organic aerosol is particularly important because it crosses into the cardiovascular system, and you get, you know, a lot of disease as a result of that. It's probably about 75% aerosol, and the rest is ozone type stuff. And also the ecosystem services are being impacted by these things. Anyway, now to some examples from SciMac measurement from space. Okay, so we started in GOM in this, but what you can see is this is the type of picture you typically see. This is a yearly average picture. And what you see is pollution, very obviously. You see, I hope you see biomass burning places, okay? And I think one of the circles has gone a bit crazy, but you also see shipping emissions, okay? And you can see roads, actually, and when you average a bit. And you also see outflow, which is very important. But in terms of air quality, I just want to say is when we looked at China, this was a big discovery at the time because the ground-based measurements were saying nothing's changing according to the people who are doing it, but over in Beijing area and around about, we see the increase. We also see, we now see with different satellites, GOM, then SciMac, then GOM2, and also OMI, we have using the same technique which we started. GOM is a smaller version of SciMac, which flew first, only making nadir measurements. But the point is we see, and this is, anybody who's been to Beijing knows what very bad air you have there. And part of it is the NO2, and basically the ground-based measurements were saying there's nothing wrong, but in fact it was very badly wrong. But they have put in a lot of legislation, but it seems to be tapering out now. That's the measurements going down to end of 2018 from Andreas Richter in my lab, okay? The new kid on the block is Tropomi in Europe. This is originally the Dutch joined the Germans to build SiteGAM, actually, and they pioneered this with ESA. It's an imaging device, so it's slightly different in this sense, but builds on OMI. But that's the situation with GOM2, which is the, built in, or designed in the 90s by people like myself and the engineers at ESA and the Indian industry. And this is now the situation, and you should see how improved resolution really helps you pick up the and this is the thing, is we want temporal and spatial resolution. This is the spatial resolution once a day, but what we want is the geostationary, and we've got to do this stuff, okay? Interestingly, we also see much better the shipping, okay? You can now see where the shipping lanes are, okay, as an example. And there's our NO2. So the ships always travel straight. You do some great stuff like this. Anyway, there's lots more, and we do a lot more molecules of interest, but I wanted to jump because of time, and you would like to get, I'm between you and coffee. So I don't want people storming out here to catch the coffee and cookies before the young people eat them. But anyway, the last problem is, of course, climate change. We're going to hear the real story from Tom Stocker, but I just want to say, measuring this from space, okay, the issue is, we're chucking out CO2. We know this since Keeling's great work, which suddenly showed sensible values for CO2. Before that, there was a longitudinal dependence of CO2 measurements, which is very strange. But anyway, what we see, the stuff is coming out, and about 50% of it stays in the atmosphere, and that's the issue. And Sayamaki has started the measurements from space, and via a failure to get CarbonSat, we're hopefully going to get a CO2 emission in the next X years. I'm hoping, they tell me 2025, but these things always take a bit longer. But we're going from the picture on the left-hand side, which is sort of one thing over Berlin, to being many, many measurements over Berlin of CO2 and methane with a resolution of the order of 2 square kilometers, two and a bit square kilometers. Okay, so this was the first definite proof that we can do this. We see that what you want to see in CO2 is you don't want to measure it, you want to measure the difference, because you want to see sources and sinks. And we were able to pick out here, this is Mikhail Bukvit's work, the emissions from the populated areas of Europe. Okay, and you can see population and you can see anthropogenic CO2 emissions on the right-hand side, and we were able to pick out, it's only 2 ppm difference, so you've got to measure small differences. It's not an issue to measure CO2, it's an issue to measure the difference in CO2 to a high level. And you see sources and you see sinks, and you see the Earth breathing. And that's sort of shown here in the bottom bit, where you see the difference between January and December. You see things growing. You see the colours changing, and basically the boreal forest. We're also now comparing here with our record from space with the ground-based measurements from NOAA, and we're also able to determine the mean growth rate, which is heavily impacted by things like ENSO. So there's a huge science field here, and what we're saying is we can do this from space, just give us the money. I did a calculation about 10 years ago which said if you put a 0.1% tax on fuel, you get so much money to build operational measurement systems, you would be laughing all the way home. You wouldn't be able to give it out fast enough, okay? And nobody would notice at the paying at the tank at the petrol station. Okay, this is a cool thing because it's seen in NO2 to begin with, but this compares Europe and America averaged and China, and what you see is a weekly scenario. And what happens in Europe is that people have time off on the weekend, but apparently not in China. So this is called the so-called weekend effect. You can see it in cities. You can also see differences between Friday and Saturday in Jerusalem and Cairo. Okay, so that's neat stuff, but kind of fun. We also looked at the differences of NO2 to CO2, because that tells us about changing fleets of cars and traffic and stuff like that. And you can see that the Chinese situation is changing compared to the US. New thing now, there's the OCO2 mission. It's not got very good coverage, but it got high resolution of the order of a kilometer. And we're combining this with NO2. This is Max Reuter looking at this. I'm nearly done. You will get your coffee. And you were able to pick out plumes. And that's the thing, synergistically, because NO2 is coming from biomass burning or from cities, so it's going to help us identify plumes. At the moment, you can see the problem is that the Sentinel-5P is much better resolution, or better coverage, but poorer resolution, and the OCO2 is great resolution, but bad coverage. So in CO2M, which I talked about, we want to get that way. Okay, and that shows that a little bit better. Okay, that's the point. Okay, now on the methane side of things, that's the last thing I'm going to go. The issue is methane. Yeah, why is, what's going on in methane? We've got these wetlands, we've got permafrost, we've got cows, we've got the issue of fracking coming up, okay, and but the point is, it was increasing, it stopped, and now it's increasing again, and we don't know why. There are as many explanations as scientists who work on this. Now, the big issue for the future, here's Sayamaki. You can see April to June and July to September methane, so that's the wetlands. But what happens when the permafrost goes? Okay, so some people say nothing. Some people say the permafrost will produce a lot of methane and CO2, and as it melts, so this is where the Earth system issues become a big problem. Okay, so that's the future. This is going to be a bomb, which will accelerate, because I'm sure you all know the global warming potential of methane is 25 times that of CO2. Okay, so just to show also, this is nice new stuff from Turkmenistan. We pointed out with average data, there's some huge sources there. They really leak it like hell. But now this is like one-day data or something fantastic. Or a couple of orbits from tropomi, so that's showing the way forward. We can do a lot better, just give us the money. Okay, similarly, this is then methane over India, and methane. India is going to be increasingly important in all of these things. Okay, just a last point to agree with my colleague previously. We've been thinking we need access to space. This is where this is an aircraft experiment on the right-hand side doing NO2 over Berlin and the satellite. Okay, and that shows with the 7x7, which is roughly what Sentinel 5 and Sentinel 5P is a little bit better, but we really want to have that. That's the 1 kilometer. What we need is global 1 kilometer every 20 minutes. Okay, and the same for methane. Here's the Central Valley in the USA. This is a load of different sources. We flew over it with our instrument, and you get very nice individual sources, including dairies and oil. Yeah, it's basically a lot of leakage. Okay, and that's, again, we need that kind of thing. So the future is kind of, we think maybe small sats. Okay, and I quite like this. This is, we hope for big science from small satellites. Thank you very much.
Thanks very much, John. Time for a question or two. If I can see people. One here.
What would be uncertainty of CO2 anthropogenic emission derived from satellite for daytime observations and including also uncertainty due to cloud coverage?
Well, cloud cover, you know, clouds move. That's the point about having geostationary. You look between the clouds. Okay, so it's a question of coverage. 10 o'clock in the morning is the global minimum in clouds. 4 o'clock in the afternoon is the maximum. So it's a question of how we do our measurement strategy. Not a problem, in my opinion.
Right. Thanks very much, John. I think we have one more item before people get their copy, which is the award of the 2019 IAMAS Early Career Scientist Medal to Lei B. Perhaps Leah and Joyce Penner could join us. Joyce Penner chairs our nominations committee, so she will say just a few words by way of introduction.
So I'm here as Vice President and head of the awards committee to present to Lei B the 2019 IAMAS Early Career Medal. Lei obtained his PhD at Texas A&M University under Professor George Kadawar and Professor Ping Yang. He stayed on as a postdoc for 4 years and then moved to Zhejiang University in China, where he's a faculty member and building a research program under his area of expertise. So this is presented to Lei B for his outstanding contribution to research on light scattering and non-spherical and inhomogeneous particles with applications in atmospheric radiative transfer, remote sensing, and climate science.
So congratulations. It's always good to see the next generation of leaders in atmospheric science. So it's been a great success, our Early Career Scientist Medal. So congratulations from me. Would you like to say just a few words?
Thank you. Thank you very much for the introduction. I must say, I feel deeply honored for receiving this prestigious award, IAMAS Early Career Scientist Medal. So my deepest appreciation goes to the International Radiation Commission for nominating me. I'm also grateful for IAMAS for recognizing my contribution to atmospheric sciences and my services to the research community. So thank you very much.
Okay, so now you get your tea and coffee. We'll press up a break for, say, 20 minutes, meeting back at 10:30. Thank you.